In this section, we're going to do or talk about applications of rational equations. The first type of application that we're going to discuss is called work rate problems. And basically, work rate problems involve two people or two objects, two machines, two people, any kind of situation like that, completing a job separately, and then will give you information on them working together. In order for us to solve these types of problems, we're really going to want to know what a work rate is. All right, and so I'm going to give this informal definition of work rate as the amount of jobs completed per unit of time. For instance, when I say per unit of time, like per day or per hour or per minute, and these are some examples here, right? I have 2 hours per 2 jobs per day, or 3 yards per hour, or 3 2/5 jobs per minute. This is what I call a work rate. And anytime you have a rate, it is going to be like per something, right? What we're going to do in these problems is we're going to actually set up a chart to help us kind of tailor our thinking. Of course, this is not a necessary step, but it helps us organize our thinking. And this is what my chart is going to look like. I'm going to have two people or two machines doing a job, and then I'm going to be given information on their ability to do the job or the time it takes them to do the job together. All right. What I'm going to need in order to find the work rate, which is the main topic of this problem, is how long it takes them to do the job alone. For instance, it may say that a person takes 3 hours to rake a yard or to wash a car. Well, then if it takes 3 hours for that person to do that job alone, then their work rate is going to be 1/3 of the job per hour, right? Because if it takes 3 hours to do the whole job, then in 1 hour, right, that's my unit of time, it's only going to take them, it's only going to be 1/3 of the job, all right? Or another person, it might take them 6 hours to do a job. Well, then their work rate is going to be 1/6 of the job per hour, right? Since it takes them 6 whole hours, in 1 hour they're going to do 1/6. If you notice these, the reciprocal of 3 is 1/3. The reciprocal of 6 is 1/6. So in order for us to find the work rate, all we have to do is the reciprocal of their time alone. All right, and sometimes we're going to have a variable in here, or actually in all these problems we're going to have a variable. And when we have these variables, well, if their time together is x, then they do 1x of the job, 1/x of the job per hour, and that would be their work rate. Let's look at some actual examples. One hose can fill a pool in 20 hours. Another hose can fill the pool in 16 hours. How long will it take the two hoses working together to fill the pool? Okay, so instead of having people, we have hoses, right? So I have hose 1, hose 2, and then the hoses working together. Okay, well, it tells us that one hose takes 20 hours to fill the pool. The other one takes 16 hours. All right, how long will it take the two hoses working together to fill the pool? Well, I don't know how long it would take them to work together. And I know this time alone column kind of seems a little not necessary for this together row right here, but their time together is X. We don't know that. That's what we're actually trying to find. Now that we know the times alone, we can find the work rate. If it takes this person 20 hours, then the work rate is going to be 1/20 jobs per hour. All right, and I guess I should put the units here. All right. Hose 2 takes 16 hours to do the job alone. So in 1 hour, they'll do 1/16. 1/16 of the job. And together, they take X hours. So we have 1/X per hour. Now that I have this is going to help me to create an equation. And this is where my equation is going to come from. This is an important part. All right. It takes this hose 1/20 jobs in 1 hour. They can do 1/20 jobs in 1 hour. This person can do, or this hose can do 1/16 jobs per hour. All right. If I add those two things together, 1 over 20 plus 1 over 16. It has to equal the same rate that they have when they're working together, which is 1 over x. All right? And we're assuming that they're going to be going the same speed. So they're going to have 1 over x per hour. Now I have an equation. This is how we're always going to set these up. You add the two work rates for the individual holes, and it should equal the same as when they're working together, right? All right, and now what I'm going to do is I'm going to solve this equation. Of course, this is a rational equation, so we need to find the LCD, right? Between 20 and 16, the LCD is 80, and then we have an x in that denominator over there, so I'm going to multiply both sides by 80x. When I multiply on my left-hand side, I'm going to distribute. All right. Now with that 20 goes into 84 times, so I'm going to get a 4x. 16 goes into 85 times, so I'm going to get a 5x. The x's don't cancel. No x's can cancel. And on my right-hand side, the x's will cancel. And so I'm going to get just 80. Well, I can combine like terms. 4x plus 5x is 9x equals 80. And then I can divide both sides by 9. And I'll get that x equals 80 over 9. And my units is hours. All right. And of course, when we write hours, we don't normally write it in that fashion. We can change it to a mixed number. That'll be 8 and 8/9 hours, right? 8 times 9 is 72. You need 8 more to get to 80. Or you can write it as a decimal, 8.8 hours. Of course, when you do your homework on My Math Labs, they'll tell you how to leave your answer. But that's one good example of a work rate problem. Let's look at another example. In this example, it says that Manny can paint a house in 5 hours less time than it would take David to paint the same house. If they work together, it would take 6 hours to paint the house. How long will it take David to paint the house if he is working alone? Okay, so we got two people here. We have Manny, we have David. And of course, we're giving some information for when they're working together. All right. And so what I'm going to do first is I'm going to figure out the time alones. All right. This time it's not as explicit or given to us as easily as in the last example. All right. They say that Manny can paint a house in 5 hours less time than it would take David to paint the same house. All right. They're telling us Manny's time alone as if we know David's time alone. And so that's what I'm going to let my variable be, David's time alone. All right. Now that I know David's time, I can come up with something for Manny, right? He has 5 hours less time than it would take for David. Well, if he's going to have 5 hours less, I have to subtract 5 off of David's time, and he has that quicker time. The next sentence says that it takes them 6 hours to paint the house if they're working together. So this time, our together time is given. Now that I have these two things here, I'm ready to find my work rate, all right? Remember, our work rate is always the reciprocal of our time alone. So it'll be 1 over x minus 5, 1 over x for David, and 1 over 6 for their time together, their work rate together. Now that I have this information, also remember that your units are hours. But now that I have this information, in order for me to solve this problem, I can set up my equation by looking at their work rates for their individual times. So that'd be 1 over x minus 5. If I add those together, the two individuals, if I add the two individuals, it should equal the together, all right? And this is a rational equation as well, all right? We need to find the LCD. Well, in order for us to find the LCD, we will need to multiply all of our denominators. They're all factored, they're all different, so all of them are going to be in my LCD. And so I'm going to multiply both sides of this equation by the LCD. Guess I didn't need this extra parentheses here, but it's fine. All right. Of course, on the left-hand side, we have to use our distributive property. And so we'll get, well, when I distribute, the x minus 5's cancel, and I have a 6x. When I distribute here, the x's cancel, so I'm going to be left with a 6 times x minus 5. And on my right-hand side, the 6's cancel, so I'm left with x times x minus 5. Of course, we want to distribute so that we can see what type of equation we end up with. Distribute this 6 here. Get a 6x minus 30. And if I distribute on this right-hand side, I get an x squared minus 5x. This is a quadratic equation. All right, I'm going to go ahead and combine these 6x's here. That's 12x minus 30 equals x squared, my subtraction there, minus 5x. Of course, with the quadratic equation, we're going to get everything on one side set equal to 0. So I need to subtract 12x from both sides. But at the same time, I need to add 30 to both sides. Okay? And so I get 0 because everything here cancels. And I have an x squared minus 17x plus 30. And of course, only way we know how to solve this is by factoring. So I have an x here, two numbers that multiply to give us positive 30. My signs are dropping off. Positive 30, but add up to a negative 17, a negative 15, and a negative 2 will work. All right. Well, I have two things that multiply to give me 0. Let's set them both equal to 0. X minus 15 equals 0. X minus 2 equals 0. If I add 15 to both sides here, I get x equals 15. And if I add 2 to both sides here, I get x equals 2. Now, we have a sort of a situation here because we have two solutions, x equals 15 and x equals 2. One of these is not going to be our solution, right? Let's go back to see what x represents. Remember, x represents David's time, all right? All right, time is in hours. So, right, we got x equals 2. Right, if x equals 2, that means I have to put 2 in for x here with Manny's time, and I get 2 minus 5, right? 2 minus 5, which is negative 3. Well, we can't have a negative time, all right? And so 2 will not be my solution. 15 will work. I won't get a negative. And so my only solution here is x equals 15. So it takes 15 hours. That's David's time. Okay. Let's move on to something a little different. The next type of application we want to solve is what we call uniform motion problems. And this is a problem that you've probably encountered before. Uniform motion is assuming that a person is going or driving or running the same speed the entire way, right? And of course, we don't do that in real life, but it's kind of making a general point here. With uniform motion, we know that distance equals rate times time. And so this is the formula that we're going to use here. Distance is for d. D is for distance. R is for rate. Okay. All right, and that's the speed, right? Miles per hour, meters per second, and T is for time. All right, and as long as I know at least two of these, for instance, if I know the distance and the rate, right? If I know the distance and the rate, then I can solve for T. I can find the T by dividing this equation on both sides by 2, right? So if I know the distance and the rate, then I know I can find T by doing D over R equals T. And this is what we're going to be mainly doing in this section here with dealing with these uniform motion problems. Again, we're going to have two situations going on. Two people might be going, driving or running, or there might be two situations. In one situation, we might be going somewhere. In another situation, we might be coming back. We're always going to have two situations. So this is how I'm going to set up my chart. Again, when there's two things, I'm going to set the chart up to help organize my thinking. All right, so I have person 1 and person 2. They're always going to have their own distance, their own rate, and their own time. And once I know that information, I can use this equation here, or possibly this equation here, to help me solve my problem. Let's look at an example. Ariel drives 15 miles per hour faster than Sharon does. Ariel can drive 100 miles in the same amount of time that it takes Sharon to drive 80 miles. Find Ariel's driving speed. Okay? So instead of having person 1 and person 2, I'm just going to put their names in the chart. So I have Ariel and I'll have Sharon. All right? This first sentence tells us something about their speed or their rate. Okay. It says Ariel drives 15 miles per hour faster than Sharon does. All right, so they're telling us Ariel's rate as if we know Sharon's rate. That's a clue that our variable is going to be the rate that Sharon drives. Now that I have Sharon's rate, I can find Ariel's. If Ariel is going 15 miles per hour faster, then I definitely need to add 15 to whatever Sharon's going, which is x. So I get x plus 15. The next sentence, it says Ariel can drive 100 miles in the same amount of times it takes Sharon to drive 80 miles. So that just gives me the distance. Ariel goes 100 miles. Sharon goes 80 miles. All right, and with this information, we're supposed to find Ariel's driving speed. So we need to figure out what this x plus 15 is going to end up being. If you notice, they didn't give us any information about the time. All right. And this is where that formula, distance equals rate times time, come into play. All right, that's going to help us set up our equation. Right? Since I don't know time, I'm going to divide both sides by r. So I get d over r equals t. And so now if I want an expression for time so I can complete my chart, well, time is going to be 100 over x plus 15. And Sharon's time is going to be 80 over x. All right, now that I have my chart, my goal is to set up my equation. Now this is very important here. And you got to look at the situation as this is a detailed type of problem. In this sentence here, it says Ariel can drive 80 miles in the same amount of time it takes Sharon to drive 80 miles. The thing that's going to help us set up our equation is the same amount of time. All right. When we see that same amount of time, that means the times are equal. These two things are equal. And so if we want to set up an equation, well, take 100 over x plus 15. That's Ariel's time, and set it equal to Sharon's time, which is 80 over x. Now that we already know how to solve these rational expressions, I'm going to allow you to solve these rational expressions on your own. I'm not going to actually do it on the video. It'll take a long time. But I'll go ahead and tell you that x equals 15. All right, sorry, 60. All right. So that means when you solve this, find the LCD, multiply both sides by the LCD, and finish solving, you'll get x equals 60. But that's not our solution, right? Remember here, we're looking to find Ariel's driving speed. Well, 60 actually represents Sharon's speed, 60 miles per hour. So if we want Ariel's driving speed, it should be 60 plus 15, which is 75 miles per hour. So that is our solution. Okay, let's look at another example. These can get a little bit more complicated. In this example, it says Dominique is kayaking in a river that is flowing downstream at a speed of 2 miles per hour. Dominique can paddle 10 miles downstream in the same amount of time she can paddle 5 miles upstream. What is the speed that Dominique can paddle in still water? All right. So we got two situations going on here. She's going downstream and upstream. And the stream is going 2 miles per hour. All right. So that's important, right? Speed of the stream is 2 miles per hour. It says she can paddle 10 miles downstream in the same amount of time it takes her to do 5 miles upstream. All right, so that gives us the distance. I'm going to go ahead and put my distance. So downstream, 10 miles, upstream, 5 miles. All right. And the only other information is speed of 2 miles per hour, and of course we got to remember the same amount of time. All right, this one is a little bit more difficult because I don't have anything about the rate that she's going, but I do get the speed of the current. All right, how far or how fast she's going downstream. Okay, so what I'm going to do, since I don't know information about her actual speed, I'm actually going to let my variable x represent her speed in still water. And I'm going to use that fact and the fact that the speed of the water or the stream is 2 miles per hour. All right. So when we're going downstream, right, you're going down, water always flows down. Right. So if the stream is going 2 miles per hour and she's going X miles per hour, then when you're going downstream, she gets that extra boost by 2 miles per hour. So I'm going to let her rate be X plus 2. All right, downstream, we get a boost. All right, upstream, water flows down, but you're going up, so you're actually going to get a resistance. And so instead of adding 2 to her speed in calm water, we're actually going to subtract 2 to her speed in calm water. And now that I have my distance and rate, I can figure out what my time is. All right, distance over rate is the same thing as time, so I'll have 10 over x minus 2, and I have 5 over x minus 2. All right, that's 10 over x plus 2, by the way, and 5 over x minus 2. All right, once we have this, we can use the fact that this problem says the same amount of time to set up our equation. Just set these times equal to each other. So I'll have 10 over x plus 2 equals 5 over x minus 2. And when we solve for x, that's actually going to be our speed in calm water or in still water. All right, I'll let you solve for x. Find the LCD, multiply both sides by the LCD and simplify. And what you're going to find is that you get x equals 6. So the speed of the boat in calm water is 6 miles per hour. Our last example involving uniform motion involves an airplane. All right, it says an airplane flies 72 miles per hour with a 30 miles per hour tailwind and then flies back with a 30 miles per hour headwind. If the total time for the round trip was 1 hour, find the speed of the airplane in calm air. All right, this situation is almost identical to the situation with the kayak going upstream and downstream. But this time, instead of upstream and downstream, we have a tailwind and a headwind. And so we're going to need to know the difference between them two. Okay? A headwind or a tailwind is the wind that's blowing to the tail of the plane first. So with the tailwind, we also get a boost. A headwind is the wind that hits the head of the plane or the front of the plane first, so we actually get a resistance. All right, and so now that we know that information, let's fill in our chart with our distance, rate, and time. I'm going to read the problem again. Airplane flies 72 miles per hour with a 30 mile per hour tailwind and then flies back with a 30 mile per hour headwind. All right, so the distance is going to be 72 miles for both directions. It says the total time for the round trip was 1 hour, right? So the total time, I can't put 1 hour, and I don't know if it's half and half, right? I don't know how much time it takes in each individual direction, but I know the total time is 1 hour, okay? I'm not given anything about how the plane is actually flying, so I'm going to let x be my speed of my plane in calm air. Now that I know that, and I know that I have a 30 mile per hour tailwind and a 30 mile per hour headwind, then I can write my tailwind, my speed when I'm flying in the tailwind as x plus 30, right? I get that extra boost, that means add. And rate for my headwind, or when I have that resistance, is going to be x minus 30. Now that I have my distance and rate, I can write my time as 72 over x plus 30. And then for my headwind, traveling in headwind, 72 over x minus 30. I have my time, and this time I'm going to be setting my equation up a little bit differently. All right? It doesn't say that they travel in the headwind and the tailwind in the same time. In that case, we set our time equal to each other. But it does tell us that our total time is 1 hour. So if I add my time for when I flew in the tailwind to the time that I flew in the headwind, it should total or equal 1. All right? So I have 72 over x plus 30. Plus, sorry about that, 72 over x minus 30. That's going to equal 1. And remember, x is the speed of the plane in calm air. Of course, I'm going to allow you to solve that problem, but when you finish solving, you're going to find that x equals 150. So the speed of the plane in calm air is 150 miles per hour. The last thing we want to talk about in this lesson is what we call variation. Okay? And basically what variation is, it's the way that one quantity changes in relation to another quantity. All right? That's what I mean by variation. And so what we're going to do here, there's 3 types of variation, and they all have their own separate equation. All right? And I'll always give you in the problem what type of variation that we're going to be dealing with. With direct variation, we follow the equation y equals k times x. All right. With inverse variation, we follow the equation y equals k divided by x. And with joint variation, we follow the equation y equals k times x times z. Okay? K times x times z. And basically, with all of these, we have y and x, except for the joint variation where we have z. But they all have a k in them. And k is basically our constant of variation. Okay? And that's something that we're going to have to find in every single problem. All right, I have some steps down here that helps us to solve these variation problems. It says determine the type of variation and write the correct equation. So after you read the problem, it'll say either directly, they vary directly, inversely, or jointly. If you see those words, you have to memorize these equations here. Pick the one that you see when you see these words here. And after that, use the first set of values in the equation and solve for k. So your problem is going to give you a first set of values. Plug those into the right variation equation here and then solve for k. And then you'll know k, and that'll allow you to solve multiple problems. So that next step says substitute k into the original equation and then use the second set of values to solve the problem. Let's put those steps into action. All right. In this problem, it says the pay that Tony earns varies directly as the number of hours she worked. All right. Notice that varies directly. That tells me I'm going to use that first equation, which is y equals k times x. All right. If Tony earned $234 for working 24 hours, this is what I mean by the first set of values. How much would she earn for working 38 hours? This is what I mean for the second set of values. All right. And so let's solve this problem. All right, the pay varies directly as the number of hours worked. All right, so I'm letting y represent how much she is paid, and I'm letting x represent the number of hours she worked. All right, now that I know I have my right equation, I'm going to put my values in. All right, $234, that's her pay, so I'm going to substitute that in for y. and she worked 24 hours. That's X, the number of hours. So I have 24 there. Now that I have this, in order for me to solve for K, I can divide both sides by 24. And I'll get that K is the same thing as 9.75. And so I've solved for K. And so what I'm going to do is, instead of writing this equation like this, I'm going to write it as Y equals 9.75 times X. That way, for anybody who works with Tony, or anybody that works at that company, I can just plug in the number of hours they work and it'll spit out how much I should pay them. So if I'm a business owner, having this kind of information is going to be very important. All right. And so I'm going to solve the problem. They say, how much will she earn for working 38 hours? Well, I put 38 in for X. And I'll get that Y equals 370.5. And that's $370.50. Okay. So it's important not only for the employer, but for the employee as well. So you can calculate how much you think you'll be bringing home. Let's look at another example. It says the weight that a beam can support varies inversely, keyword here, as its length. If an 8-foot beam, okay, can support 630 pounds, that's my first set of values, how much weight can a 5-foot beam support? That's my second set of values, all right, or my second value. And so since I see that this varies inversely, then what I'm going to do is write my equation, Y equals K over X. That's why it's going to be very important for you to memorize the actual equation that you're going to be using. All right, notice the weight came first, so weight is Y and length is X. All right, and so what I'm going to do is I'm going to solve for K using these first set of values. 8 feet, feet is a length, and I have 630 pounds, that's my weight. So I get 630 equals K over 8. In order for me to solve for K, I can multiply both sides by 8. And I'll have that K is the same thing as 5,040. And so instead of writing my equation as Y equals K over X, I know that K is 5,040. So I get Y equals 5,040 over X. Now what I'm going to do is I'm going to answer the problem, or solve the problem. It says how much weight can a 5-foot beam support? Well, remember 5 feet is length. Length is given by the variable X. So I have Y equals 5,040 over 5, which is the same thing as 1,008. Y is weight and it's given in pounds. So 1,008 pounds. One last example for this video. This is getting pretty long. And this is one that has joint variation. And joint variation is a little different because it involves actually more equations. All right, it says Y varies jointly as X and Z. All right. So one thing, for one, that tells me the type of variation I'm going to have. So it varies jointly as X and Z. If Y equals 70 and when X equals 10 and Z equals 6, those are my first set of values. Find Y when X equals 3 and Z equals 8. That's my second set of values. Okay. So joint variation, Y equals K times X times Z. Got to solve for K, so I'm going to have 270 equals K times 10 times 6. That's 60, right? So to solve for K, we can divide both sides by 60. And of course, those cancel. And so we get that K is the same thing as 4.5. And so instead of writing Y equals K times Z, K times X times Z, we're going to have Y equals 4.5 times X times Z. And so now we can go to our second set of values and solve for Y, right? Which is asking us to solve in the problem. X is 3. So I get 4.5 times 3. Z is 8. And if you multiply those things together, you're going to get 108. And of course, we don't have any units in this problem. This is generic. All right, and so that's pretty much variation. All right, and this concludes our lesson on applications of rational equations.